So please, we're not that many people in this really big room, so maybe if you want to move a little bit forward, it will be nice and cozy. But if you want to keep your distance, it's quite all right. I can take that message. It'll be easier for you to do your emails. Thank you for coming. The idea behind this track was that everybody's using mobile phones and data these days. We all run around with our little PDA, and a lot of people of us have absolutely no idea what goes on behind it. At the same time, some of us runs IP backbones and networks, and suddenly we see that different types of traffic is running over it. So that's what we're trying to cover today. First, I'll do like a little, this is how mobile network works, 101 for kindergarten level. So if any of you knows anything about telephony, you can do your emails in that time. And then just to make sure that we all on the same level as I am with regards to mobile networks. After that, we will try and have a look at what happens when you decide that your mobile network is usually running over SDH and all that kind of old-fashioned transport, and you decide to use your IP core for that. What happens when you're an IP operator and somebody does that? And we'll have Jan talking about that. And after that, we will move to the mobile data part, where David is going to talk about what is going to happen with the access that is actually provided by the mobile networks. And then we wrap up in a discussion of the topics that we have covered and what consequences is that going to have for us as IP operators. So that's the idea. And I'll try and start out on the basic mobile network. So what we're going to try and tell you about is basically what is a mobile network and how does the call working, the whole call setup. How does this mobility thing works? Because you may have noticed that you can drive your car and talk on your mobile phone at the same time. Might not be good, but your call will still be there. You can also go to other countries and your phone is still working. What is the technology behind that? And finally, the whole mobile data. It uses the mobile network, and you can also go to a foreign country and your mobile data still works. It sucks, but it works. So how does that work? That's basically what I'm going to try and tell you. So the definition of a mobile network is that you have devices where your access is a radio link to an antenna, and where you can keep the connection even though you move from one antenna to another antenna. That's why Wi-Fi in this brief overview is not a mobile network. And another thing that you need to be aware of when we talk about this is that the spectrums, the frequencies that you use for the mobile systems are licensed. An operator has to pay for a license. And they're limited, they're heavily regulated, and they're very expensive. So that gives us a lot of demands to the technology that's used behind it. Again, this is how is a mobile call set up. So when you turn on your phone, it registers to the antenna that's closest and strongest to the device. And that means that when a call is placed, that's going to reach that phone. There's some back-end systems that actually knows, oh, the phone is connected to that antenna and will direct the call to there. And when you move around between antennas, still the phone registers to a new antenna, and then the whole back-end system registers that, oh, I have to direct the talk or the data to some other antenna. And for some reason, they figured out to make that happen without interrupting the sessions that takes place. That means there's a lot of back-end systems for all this to work, and those back-end systems are in what is called the mobile backbone. So it consists of, you have the antenna, the access network. The antenna has some controllers, and then you have connections into the backbone where you have the voice part is on the top of the slide, where you have the media gateway and the controller. That's basically forwarding plane and control plane and the router. You could combine it two, maybe. And then the data is you have the antenna, the base station controller, and then you have some aggregation nodes, and then a gateway to the internet, roughly. So one of the more interesting part of it is that you can roam. You can go and use your device on another operator's network. You can only do that when you have a roaming agreement between the two networks, but that is a very important part of running in a mobile network, is to make sure that you have roaming agreements with enough networks around the globe so that your users can travel around and still use their phones. And this is, again, is all these systems are taking care of. You register. The foreign operator sees, oh, this is not one of my subscribers, but it's a subscriber from one I have a roaming agreement with, and they send a notification to the home network that, hey, your phone is in my network, so you send the traffic here. Basically, that's how it works. And finally, mobile data, the thing that we all use. We run around with our little phones and we want to go to the internet on it. So how is the traffic routed? Does it just go to the antenna and then out to the internet? No, that's not the way they fixed it. So the packets go from your device to the antenna, and then it goes via some access network. Usually, sometimes it's fiber, but usually it's ATM T1s or E1s that you use. And then it goes to your internet gateway. That's usually a central device in your network. You have like maybe one or two of the typical operators, and then from there it goes into the internet. People often complain about delay when they're using their mobile devices, and that is because there's a lot of delay just getting from the mobile device up to the antenna. You can sometimes have somewhere between 50 and 300 milliseconds. And so it doesn't really matter, then you have to route the rest of the traffic 50 or 100 milliseconds more. That is basically what the designers thought, is my personal opinion. Another thing that we often talk about when we have the mobile access is that all the users in a cell, all the users using one antenna to connect to the internet, is sharing the bandwidth of the antenna. And the typical antenna these days is around 7.2 megabit. So if you have like 10 users there, it's not much bandwidth there compared to a DSL line. So that is one capacity restraint that you have. Another one is the bandwidth connecting the antenna. Because in my network, we use a lot of E1s to connect to the antennas. But if you, as a user, is expecting to be able to download something with 7.2 megs and you only have 4 megabits connecting the antenna, you're only going to get 4 megabits out of it. And that's only if you're the single user on the antenna. So that are things that people need to be aware of when they hear about the capacity that's available from mobile operators. And finally, my final slide in this one is the mobile data when you are roaming. This is a really interesting way of they decided to design that. So I made a little drawing of myself right now. Yeah, I forgot to mention, but I'm Nina, I'm from T2C, and that's based in Denmark. So I'm Danish, and my phone belongs in Denmark. So when I'm here in the US and I want to see CNN.com because there's some interesting international news I want to see on my mobile phone, my phone connects to some antenna out here, and the foreign network recognizes me and I can roam there. But in order to get the data to the internet, the packets goes from the mobile network up to what was called a GRX provider, which is the mobile internet. And the GRX providers have peerings, and they have 3 places in the world where the peerings can take place. Somewhere, I think it's Hong Kong in Asia. Singapore, sorry, thank you. And it's Ashburn here in the US, and it's AM6 in Europe. So this peering will probably take place in Ashburn, if we have the peerings up there. Otherwise, it will go via the first GRX provider to Amsterdam, and then it will enter into the TDC GRX in Amsterdam, and then go back to Denmark into to the TDC mobile network, and then to the internet gateway. This is where the packets will enter the public internet. And I wanted to see a CNN site that's hosted in the US. So now the packets goes via the public internet, back over the Atlantic, hits the CNN, and then I need to get the downloaded data all the way back. It creates a little delay, and sometimes it loads the pages a bit slow. Yeah, any questions? There's a question.
Hi, Patrick from Akamai Technologies. When it goes across the GRX, that's actually IP-based, right?
It is, but it's it's a VRF, usually.
Right, but what I mean is the data is now unencapsulated from whatever cell packet it is in.
It is, it's IP, yes.
So theoretically, if TDC has, a router on AM6, let's say, and is pairing with, I don't know, T-Mobile or whatever you're using here at the AM6, when your router gets it at the AM6, and you could just turn around and pass it right back over the non-VRF to AM6 part to the internet, or does it have to actually go all the way back to Denmark to get out to the internet?
Actually, it's not just IP traffic. All the traffic is encapsulated within a tunnel called a GTP tunnel, which is kind of like GRE, but something different because it's used for mobile networks. So basically, you run a GTP tunnel from what is called the SGSN in the network you're visiting. In this case, it would be maybe AT&T's SGSN here in the US. You run a GTP tunnel through the GRX network to the GDSN, which is the other end of the tunnel in Denmark. That's what Nina called the internet gateway on the drawing. That's the GDSN. So basically, the tunnel will be between these two devices and will not contain the end user IP address.
Okay. And this also passes things like text messages and MMS and stuff, right?
It does passes MMS, but not text messages. They are sent using the signaling plane, basically SS7.
Right, that's where the 140 comes from.
This is Anton Capella from Voxa.net. Just one question to ask about the GRX. I hadn't heard the term before, but you mentioned it is the kind of the combination of GTP between providers, GGSNs, right?
Yes.
Yeah, it's between SGSN and
SGSN, okay.
and GGSN.
The visited SGSN and the home GGSN.
Yeah, exactly. Yeah,
okay.
and the GRX is the GPRS roaming exchange.
Got it. So so is that is GRX a business idea or an agreement thing more than a physical protocol?
It's definitely a business idea.
Okay.
Basically, back in the days, most operators used to do VPN tunnels to each other, and say if you have 200 networks you had an agreement with, you had to set up 200 VPN tunnels, and of course that wasn't really manageable. So you got into the GRX idea, which is kind of like transit.
Got it. But that's provider to provider, right? That's not something you can go to an exchange and say, I'm here, who can I talk to? But it's even worse than that. I'm getting the impression that that's the case.
Well, basically you can start up as a GRX operator. Within TDC, we are actually both. We are a mobile operator with one AS, which is different than 3292. And then we have the TDC GRX, which uses 3292, but could use another AS. Most of the GRX operators use their public well-known AS, and most of the operators get a private ASN from the GSM Association.
I see, quite formal.
So actually TDC Mobile is AS 64581.
Okay. So there's a separate numbering scheme in this group of participants to identify them as a carrier within the forum or within the participating members? Is that what you're pointing out? It's like another level to like an autonomous system just for the GRX stuff?
That's
Okay.
Yes, since it's a closed system, you can more or less just use whatever AS you want. Of course, you have to keep it coordinated through the DSM Association. But it's actually just like a huge Excel arc, which isn't that huge. You can download and see whoever got what AS. There's no who is service.
Okay, makes sense. The clouds are good, but condensing them is also good for my brain. So thank you.
So to say it in layman's NANOG terms, it's an exchange point for mobile operators, and there's all kinds of interesting details that some people might like or might not like, but it's really like an exchange point. But of course, there's limited geographic coverage, which is of course an issue for packets traveling around quite a bit. And because everything is IP based, there's no real requirement to use it. I mean, you could exchange the traffic somewhere else if you would like to.
Dan McGrain from Max. Yes, there's lots of complexities. One of the players that you left out are the cell tower operators, right? So typically the cell tower operators, the networks that you think of are actually the clients of the cell tower operators, right? And so they will actually provide the backhaul and then, you know, to the provider routing points, right? So they're a kind of player in there too. So if you sort of think about how much bandwidth is available, it's really kind of, it's not just how you get, it's the aggregate of what you get off of each cell tower, but there's also basically how much is provisioned going back to each one of the routing points, right? So for example, I heard the Verizon Wireless director of their architecture once moaning about the fact that he can't get the cell tower operators that he is subscribed or is a client of to give him enough bandwidth to the towers that they operate, right? So that's a kind of a constraint, that exists in the system too, kind of institutional constraint.
Yes, thank you for pointing that out. Okay, any more? Yeah, so that was basically what I had to say, and I'm going to leave it to Jan.
Yeah, good afternoon. My name is Jan, and just like Nina, I'm from Denmark, and this is why I have this kind of strange accent, but if you can understand me anyway. TDC, yeah, we are 3292, and since a lot of you here are probably into peering, you know that already, but we also, a phone company, has been that for a number of years. We are the former monopoly of Denmark and has been operating in the mobile world for, I don't know, 20, 25 years, starting with what was called NMT, which was a Nordic mobile telephone network that was decommissioned a long time ago when we started to do GSM. The mobile part of TDC was operated as a separate company that bought transmission from the fixed-net division of TDC through a wholesale agreement. But at some point it was decided it was probably time to get the two operations closer to each other, and as part of that agreement, we started to do all of the IP work for the mobile division. I come from, as you probably guess, from the fixed-net division of TDC and work in an IP system group. About a year ago, as part of an outsourcing agreement with Ericsson on the mobile network, it was decided that we should build a new mobile core. And when I talk about the mobile core, it's not an IP core, as you know, with Juniper and Cisco routers, but it's actually, if we go to this slide, which you might recognize from Nina's presentation, the core network is basically the MSC and the media gateways. I don't know if I can, it works, okay. So this is actually the core part of the network on the voice side, but we also have the packet core, which is the SDSN and DDSN, which was discussed right before. I've been with TDC for more than 10 years and I've been more or less doing different kind of IP stuff all the time. So when I got into this mobile thing some years ago, it was very different from what I was used to. Basically, it's a very, very closed world. When you start to get into IP, there's tons of resources out there. There's mailing lists like NANOG and the various NSP mailing lists. There's IRC, and there's plenty of books you can go out and buy and learn about stuff. And this is really kind of different. It's a very, very closed world, and a lot of people seem to rely a lot on the vendors. Most people tend to more or less build their own IP network. They go out, buy the boxes, and put everything together themselves. But there seems to be very much of a turnkey or black box way of doing things among many of the operators. There's not any public mailing list, at least not to my knowledge. If you're a member of the GSM Association, they run some mailing lists, but it's a paid membership, and it's more like a working group mailing list, as in, you know, from RIBA or IETF, etc. The conferences, I've actually never been to a mobile conference like GSM World, but if you look at the agenda, they seem to be very much focused on the business side of things, which is, of course, important to keep the business going, but being more interested in the technical side of things, I don't think there's much to gain there. And of course, people think in circuits, they think in end-to-end connections, and really don't think the way that we do with packet-based networks. The user plane and control traffic is often kept on separate interfaces in the network, meaning that, for instance, a call could flow one way through the network, while the signaling to actually make sure that you could set up the call takes another route through the network. And finally, they had decided that a phone is actually called a terminal. And that can be kind of confusing, I think. So if I mention a terminal, it actually means a phone or a PC data card. So what we'll be covering is our work on putting our new mobile core onto IP. This is how the network looked about a year ago. This is supposed to show the number of different nodes in a network the size of TDC, and also the kind of transmission that is used. If we start on the radio side, we operate more than 1,000 cell sites, both on 2G and 3G. And to control the 2G base stations, we operate about 25 BSCs, the base station controllers, that manage the 2G cell towers, which happen to be called a BTS. At the end of the presentation, there's like a small dictionary of strange mobile abbreviations. So in case you forgot half of them by the end of the presentation, you can read out. Then we have the RNCs, which does more or less the same as the BSCs, but in the 3G world. And from there we split into voice and data, voice being in this upper part and data in the lower part. The first things that we put on IP was these two nodes, and especially the interface between the media gateways. That is to carry all the voice traffic between different locations in the country. So if we have a call being set up between two phones within the same area, the voice traffic will never leave the media gateway to another location. However, if a call from one side of the country to another part of the country, the traffic will go from one media gateway to another gateway, and then finally back to the other phone. As you see, there's a lot of different transmission here. There's a lot of TDM-E1s. There's a lot of ATM. There's even some frame relay. So whatever we got, we more or less use it. This is the state of our migration as of more or less today. All of this stuff up here is running on IP and Ethernet. Down here between the SDSN and GDSN, that's been Ethernet all the time. Then we are putting the data interfaces to the SDSN on IP, both from the BSC and from the RNC. And we are also doing some deployments of IP to the cell tower. That is what we call IP in the RAN. This part out here is called the RAN, the radio area network. And that's, of course, where we need to deploy thousands of connections. We are doing that on fiber to make sure we have sufficient capacity to the towers, also for future technologies that will allow us to run much higher speed than 7.2 megabits, as Nina mentioned. Some of the requirements we were met with was that the network should be very reliable, and that really can come as a surprise. You want your cell phone to work all the time. You want really fast failover. Most people can live with something like about a second of dropout in case you have an issue in the network, because that's what we're used to when we're driving around. We have short drops of voice, and about a second is okay. We need a few QoS classes to make sure that the traffic gets the correct priority in the network, with the voice being the highest priority using EF, signaling in the middle class in AF, and data is just forwarded as best effort. We need to handle a tremendous amount of packets per second. Since these are RTP streams with very small payload, we'll get to that later, but we should handle hundreds and thousands of packets per second on the interfaces. And of course the jitter should be low because, well, voice doesn't like jitter. And finally we should be able to keep up with the growth. Voice isn't growing that much in the magnitude of 10 to 15% a year. However, data is growing tremendously. I put 100% a year in this slide, but just during the month of October, our total data traffic has been growing about approximately 20%. So it's going really, really fast. More requirements. We should be able to handle 50,000 airlines, and airline is telco speak for an active call. So basically 50,000 active calls in the network and almost 15,000 calls from the business side of the network. Packet loss should be kept minimal. We were also met with a pretty strong, short timeline. Actually, from the day we were requested to build the network, we should be in operation with the routers and switches in 10 locations in about 3 months. The main focus from the beginning was to support what was called the NB interface, which is the interface between the media gateways. And finally, we should be able to support connections to the cell towers, the IP RAN, and finally other interfaces to come. Just a brief list of different scenarios that we thought about. The two first ones are kind of dumb, but I think I would mention them anyway. This one relies on using all the existing connections and just putting routers in the end. So basically keep on using ATM and maybe even E1s for transmission and just putting routers in the end. It's of course expensive since you need to go out and buy a lot of new stuff. You will end up with a hub and spoke design of your network, which isn't really the way to build an IP network. The positive thing is we could reuse existing circuits, so there would be no lead time on provisioning new circuits. We could use dedicated equipment, so we could basically pick the best equipment for the solution. And we would have no constraints on things like software versions, configuration, supported routing protocols. For some reason, all the nodes, especially in the packet core part of the network, just love to talk OSPF to the outside, and we really prefer to use BGP. Yeah, and I think actually some operators have been doing this. This is a slight variation where we build a network from the ground up. That was based on the thinking that this is actually really, really, really important to keep the network going. We have more than 1 million subscribers in the network, so it's supposed to be really stable. In this scenario, we can go and pick the best transmission. We can use VDM, Ethernet, SDH, whatever we want. And also make sure that the layout of the network is suitable for an IP network and not the hub and spoke as we saw before. This is a slide showing our current network, access network for residential customers and also for aggregating traffic from our residential DSLAMs, which basically contains a layer 2 ring of Cisco 4500s connected to 2 Juniper M320s acting as PEs. And this was, of course, something that we thought a lot about if this was good enough to use, because it's a very widely deployed network with more than 1,000 4500s deployed around the country. So we will always be close to whatever equipment we need to connect. So it would be cheap since the network is already there. We could use all our existing provisioning tools. On the downside, this is a pretty busy network, and we add a lot of customers every day. There's a lot of changes made to the network. A lot of work is being done from the NOG to identify problems with customers and things like that. And finally, there's always the problem with broadcasting the layer 2 rings. But also, from the beginning, we knew that something might come up that required us to make kind of special configuration to the routers to do stuff like fast reroute or link coloring or run other router protocols or something like that. So we wasn't so keen on putting it on our basically major network because that would require changes to be introduced on all of the routers and switches in that network. But we did up in using this network to connect to the RAN, basically to the cell site towers. We're still doing that as a trial with just a few sites, but it seems to work pretty good. So this is what we ended up doing. Since we have an existing core, an existing distribution that has been running very, very stable, and these are kind of expensive boxes. So the idea was to reuse that part of the network and then put in dedicated PE routers and dedicated switches. This more or less gives us the best of all worlds, reusing a significant part of the networks, but still being able to do what we want on the edge. So we go ahead and reuse our existing distribution, which was at that time part Cisco GSR and one part Juniper M320s. The GSRs has since been swapped out, so now it's all M320s. We happen to have a lot of Juniper M10Is in stock. This is kind of an old router, but it does forward a few gigabits of packets, and it does that in hardware, so it can keep up with the high demand for packets per second. And they were laying around, so they were kind of cheap to put into production, and also there wasn't stock, so we could meet the timelines. And we were actually able to, when everything was in place, to put all of the new core into IP in about 1 month. So this is a very simple design that we choose to go with. The Juniper M10Is here as PEs, Cisco 3550s as switches, and then connecting to our M3 trenches in the distribution. So, so far so good. We managed to get things up and running, but of course, things doesn't always work just as expected. So now we are going into the operational part of the presentation. So to start out with something good, using dedicated routers has been a good idea because we had to introduce some special configuration. We were able to meet the timeline, and it has been running pretty stable. Normally, all the voice traffic is transported through the network using compression, using a codec called AMR. However, for debug purposes, it was necessary to use uncompressed voice at some times using PCM coding, which actually takes up 7 times as much bandwidth as the AMR coding, which of course put a huge impact on the network. And during that time, we ran into some new issues. Also, we learned that an M10I with full customer routes really doesn't do sub-second failover. That probably doesn't come as a surprise, but we needed to get around that. Also, our QoS profiles for backbone links didn't really cope with that huge amount of EF traffic that got onto some links, because we had some dedicated backbone links running into the PEs that got to carry more than 50% of EF traffic. Then it turns out there's some QoS issues and 10G cards in Juniper. And finally, you should really be aware of the overhead on packets with just a few bytes of payload. All right, fast failover time. As I told, the M10I really doesn't do sub-second failover with full routes. But since we're just using this router to do MPLS VRFs, we don't need the full internet routing on the box. So we can go with just a default. So internet is only used for management and copying software into the box, etc. So by doing that, we get into the 1 to 2 second range, which is kind of okay, but not really good enough. So what we decided to do was to configure a backup tunnel. So in case we have a link break, we have a pre-configured tunnel, so we can get the route into the into the routing table just right away and get very fast failover. Since we did that, Juniper came up with something, I think it's called local repair. So the router can do this by itself, and I think it's in Juniper 9.5. Someone is here from Juniper, maybe they can confirm if it's 9.5 or 9.6, but it's around there. We got a special build from Juniper at the time when it wasn't officially released, and we did test this in our lab, and it seems to work pretty good. And one very good thing about it is that you don't, in case you change your distribution router and you have the LSP set up to a loopback address. So if you change the loopback address of the distribution router, you will actually break the backup tunnel if you don't remember to change the configuration, which we forgot at least one site. So this is let's call it the primary LSP, which is automatically set up, and this is the backup LSP. So this is the configuration. We added, actually, there need to be, we need to configure link protection under RSVP as well, and I forgot to put that in the slide. You can see here, this is the primary LSP, and this LSP with a strange name called bypass something, is the backup LSP. By using this configuration, we can get down to, I don't know, a few hundred milliseconds failover time. QoS and EF in the backbone. So how much EF do you got in your backbone length? 5, 10%? Our idea was that we would probably never get above 15%. So that was how we had our configuration set up, and on the GSI it was even polished that way. So in case we got above 15% of EF traffic on a link, we would simply start to drop traffic. And since we were running up to 50% EF traffic on some links, of course we needed to change that. On the GSR, we simply created a new dedicated policy map to do this. This is the link utilization. I don't know if you can see the numbers from the back. So this is the megabits per second on one link in the network. And the reason that the traffic is asymmetrical is because we are using route reflectors, we will get all this traffic in through one router while we are sending traffic out in the network through two routers. So if you look at the other router, it will have the remaining traffic. This is the amount of EF traffic. Oh, sorry, this is the amount of packets per second, and you see on a link that's loaded to about 80 megabits, we see up to 120 kilo packets per second. So we're talking very, very small packets here. And finally, this is the amount of EF traffic with almost 70 megabits out of about 80 megabits. The remaining being the signaling and also a little bit of data from the BSCs. The BSCs are connected to the same routers, but since the majority of the data actually originates from the RNCs, it is not part of this. This graph shows the difference on link utilization when changing from uncompressed to compressed. And if you put this on your network and you want to handle PCM, uncompressed voice, you really need to have a lot of spare capacity. Here you see the traffic growing by a factor of 4 or 5, but looking at the entire network, we saw the traffic grow by a factor of 7. And AMR, basically compressed call, takes up about 29 kilobits of bandwidth, and an uncompressed takes up 200 kilobits, so it's a huge, huge difference. So at some point we needed to upgrade some links and put in some... Yeah?
I have a comment there. But yeah, the only thing is, of course, that if you're talking about uncompressed voice, is that over time, if you see growth rates of 100% for the regular IP traffic and growth rates of like 15% for voice, and over time, even uncompressed voice becomes very little compared to the rest.
Yeah, that's correct. But at the moment, at least the data traffic is forwarded as best effort and not as EF. Yeah. And of course, we know that the M10Is won't scale forever, and we are already looking into new platforms to handle the traffic. But since we needed to get going so fast, we needed to use whatever we had at hand. And I think so far the M10Is have been doing pretty good, but it's it's definitely not something that will scale beyond maybe a year from here. At some point, we needed to upgrade some links to the distribution to 10G, and it turns out that the IQ2 cards in Juniper, they do some default QoS config on the interfaces. And in combination with our QoS config, it means that the EF traffic ended up in a 5% queue. So basically, when we exceeded 500 megabits of traffic on a 10G link, we would start to drop traffic. That was something that happened during the period where we were running PCM, because we will never get close to that amount of traffic when using AMR. And here you can see the default configuration. If you choose show class of service scheduler map, you can see these schedulers called default something. And the EF traffic goes into this 5% queue. So basically what we end up doing is just configuring traffic manager mode egress only, and we will only do egress QoS. It's just something to keep in mind that you really don't want. If you want to run QoS, make sure that it runs in the way you want it and not in the way that your vendor wanted. So this is one. Size does matter. Here we are looking at one packet of AMR coded voice. It has 31 bytes of actually voice payload. Then there's a number of headers for NB, which is again the interface between the media gateways. Then there's RTP, UDP, and IP headers, and we end up with 74 bytes. But to get the entire frame, we still need to add FCS, Ethernet frames, the VLAN tag, MPLS headers, and some other stuff, and we end up with approximately 42 additional bytes. So that means for NB traffic, we will actually have 56% of overhead on the layer 3 packet, while looking at, again, a 1K packet is pretty average to see in the network. We'll only see 4%. And that means on a gigabit link, we can actually saturate the link with just 641 megabits of traffic. And we saw that happen with approximately 700. And the reason we could go to 700 is, again, that not all traffic is NB. We also have some signaling and some data running on the link. But you sit down and you look at your MRTT graphs or RD tool graphs and see, well, this isn't close to a gigabit, but we're still dropping traffic. So another thing we learned, and I might be the only one not to know that, but it seems that when looking at interface counter, that Juniper, they only count the layer 3 part of the packet, while Cisco count more or less the entire frame. So of course, when we look at our graphs and the SNMP counters we are seeing from Juniper, they came only from the layer 3 part. So the actual load on the link is much higher than what we expected. That also explained why we at some point saw different amounts of traffic looking at, we had a link running between the M10i and the GSR, and the GSR showed significant more traffic than the M10is, and kind of wondering where did that traffic go since it was running on a point-to-point link. And finally, if you go out and look on the Cisco switches, you will see even a different amount of traffic. So it can be kind of confusing. But it's something that you really need to keep in mind if you're running Juniper gear or other vendors that maybe doesn't include the whole frame, and you're running a lot of small packets in your network. So, so far so good. This stuff has been behaving pretty good, but of course we didn't do it exactly right the first time. And one stupid thing we did was to put everything into separate VRFs. So basically we have a VRF signaling, that's okay. But then we have a tons of other VRFs out there. And we shouldn't really have done that, because we're looking into a future where the network will be more flattened, especially when we start to talk LTE. But also we have something called 3G direct tunnel, which is the red line down here. Basically, normally when you're doing data, GPS data, you will have a GTP tunnel going to the SDSN, and from the SDSN to the TDSN. But really the SDSN doesn't do anything to the data or to the user plane of the traffic. So what you actually can do is, from the RNC side, you can split the traffic into two tunnels, one that does a control plane that goes through the SDSN, and one that bypasses the SDSN with the actual payload. And that gives you better performance and lower latency. So in the upcoming month, we are going to merge a number of these VRFs back to one. So basically, we intend to end up with 3 VPNs. One to handle all of the signaling or control plane, one to handle all of the, I think we'll probably call it a media VPN, that will handle all of the interfaces not directly connected to the cell towers, and then finally a separate VRF, especially for the RAN for the cell towers. And the reason to do that is that the cell towers are placed in not so sure locations. So in case someone breaks into a location and manages to connect to the switch where the node Bs are connected, it's probably nice to have it in a separate VPN. And also, this is definitely the way to support LTE in your network. And finally, we've been facing some issues regarding that the RNCs on some ports are actually a layer 2 device and not a layer 3 device. So they want to do spanning tree and other stuff like that and interact with our switches. And to avoid that, it would really have been great to have a combined layer 2, layer 3 platform like the Juniper MX or the Cisco 7600. So we're definitely looking in that direction for a new platform to replace the M10Is. So this is the dictionary part with all this strange word. And finally, any questions?
Anton Capella from Voxel, and I love wireless. Have you guys looked at like anything besides expensive stuff for LTE or anything backhaul wise, like higher speed DSL, reseller access, and in some countries I'm told you can do clever things you can't do in the US necessarily. Yeah, we are currently reselling bandwidth to another provider. We've also been looking at DSL, but really it doesn't scale that far, and also it's kind of asymmetrical, and probably too asymmetrical to support what we're doing. At the moment we can do VDSL to maybe 20 or 30 megabits, but it really doesn't scale that far. And also it turns out that the towers we have biggest problem to reach using fiber is also the towers that are too far away from the DSLAMs to get any significant speed on DSL. We're still thinking about if there might be some corner cases where we will go with it. We're of course also looking at microwave links, but we will try to do as much fiber as possible. Sounds good. And it's interesting you mentioned upstream versus downstream. I was assuming that if the tracking is towards more data applications than voice, maybe you might see a change in that ratio. But have you seen anything like that? We'll definitely see much more data. And at the moment we are seeing about 1:7 ratio and up and downstream, which is of course a significant difference. There's also one thing to keep in mind, that is that you need to keep clock on the cell towers, not NTP time, but clock for sync. And it's really hard to do synchronization over an asymmetrical link. I know some vendors can do it, but I don't know how good it actually works. There's a standard called 1588 version 2, which seems to be the one winning at the moment. So even if the user traffic for IP isn't demanding much upstream, you have other mitigating factors that kind of dictate what you're going to have to do for backhaul in some ways. Is that what I'm getting? Yeah. Okay. But actually, yes, I think when we started to look at things, because we do have a lot of fiber already, we have to be a pretty big operator in the business fiber area. So we have a lot of fiber in the ground already. And in general, the towers that are hard to reach, they're simply too far away from the DSLAMs. And if we need to deploy a new DSLAM close to the tower, we'll of course go all the way with the fiber. Excellent, thank you.
I know this is an old argument, but what are the chances of large...
Who are you?
Dan McGorian from Max. What are the chances of large MTU in this world, or is the small MTU set all the way out at the RAN, and so there's never a chance that you're going to be able to do anything about that? I mean, you're talking about how you're getting eaten up by packet overhead, you know, as you try and do large data stuff. It's a classic argument for large MTU.
I don't know. I don't see it change really.
Everybody punts on that.
Yeah.
Yeah.
Of course, you could add an additional layer of encapsulating or tunneling and stuff all of the small packets into some bigger tunneling packets, but I think it's way too complicated already.
I can tell you that a large amount of the microwave backhaul gear is not capable of larger than 1,500 byte
Right,
packets.
so you've got a legacy issue of until all that, and probably nobody's ever changing it anyway, so even the new generation probably isn't either, right?
Probably. I mean, the stuff we're buying isn't that old. It doesn't do it. So.
Hi, Tom Scholl, AT&T. I had, I guess, two questions. First one is, all the internet traffic has to go back to a GGSN, and then it finally gets routed out to the internet. And if you have a really large geographic area, chances are you don't have GGSNs everywhere, and there are probably only a few. And that would probably make, you know, the user experience browsing the internet and whatnot somewhat not all that great, because you're being backhauled to another part, and then you finally reach the internet, and it adds latency. Is there anything, I guess, you know, besides the LTEs eventually coming out, is there anything in the interim that says, well, why not distributed GGSNs or make it smaller, cheaper, nicer GGSN that you could at least get out there so your bits don't get hauled around as much?
Yeah, I guess we are actually a pretty small country, so we don't have to deal with that. We're only like 5 million people, probably being smaller than several of the states over here. So we don't see that as much of an issue, but of course we could start to deploy more DGSN. Then something come into place with how would you actually distribute the DGSNs, and can you keep a common pool of IP addresses, and how to handle that, and some vendors are not really good at that. So at the moment we have a significant overhead of IPs allocated to the DGSNs because we needed to have sufficient IPs in case one of the DGSN fails. And we would really love to have some more modern gear that could actually support a pool of IPs.
Okay. And then the other part you mentioned was like rapid convergence with doing some of this. I'm just curious, have you actually seen what are the actual application requirements and what works in reality? Like 50 milliseconds, does it have to be that, or can you do a couple hundred milliseconds? Where do things typically break?
It normally breaks during the discussion with the people from the vendor and from customer service, etc., because we can actually sustain a pretty long downtime without breaking the system. Normally people tend to hang up a call after approximately 2 seconds of silence and say, okay, we lost the signal, and try to call back later. But in general, we try to keep it below 1 second, basically have some leeway up to 2 seconds. But we can actually break the stuff for a number of seconds without actually tearing down the call. So not often it will be the end user actually hanging up.
Oh, okay. Thank you.
I know I don't look like it, but I'm Martin Levy from Hurricane Electric, and I would like to ask you about IPv6.
Yes? Yeah, in what context? Because we can talk about a lot of IPv6. Do you think in the context of GPRS data, getting IPv6 on your telephone, or do you think about using IPv6 for addressing the cell sign towers, or just IPv6 in general?
Well, we've just had a very long couple of talks, and the words IPv6 were not mentioned once. In some places, like in Asia, you know, they're going all IPv6 on their phones. This is not a minor upgrade. You know, the phones are far harder, the handsets are far harder to upgrade than other things and stuff like that. So,
basically, we can do IPv6, and I've been doing some testing. Our GGSN has been supporting IPv6 for quite some time. Also, for instance, this Nokia phone does IPv6. Unfortunately, it does IPv4 or IPv6. So if we could live in a pure IPv6 world, we could start more or less to deploy it tomorrow. There's some things missing regarding, we have what we call service-aware charging, basically meaning that if customers go to certain websites, we won't charge them. For instance, our own portal, and we could run campaigns saying, okay, you can go free to Facebook or Twitter or something. And our GGSN cannot actually support service-aware charging on IPv6, but it actually works, and I can browse, say, IPv6.google.com from my Nokia, And that works without running any special software on either the phone or the GGSN.
And so from my experience, from what I've seen, is that it is not necessarily that hard to enable IPv6 in most mobile networks. But of course, after enabling, you run into basically all the same problems that any other operator in any ISP network that you have, and that's basically all those application incompatibilities, devices that don't support IPv6 yet. But the network itself seems to be in most cases in fairly good shape already, and it shouldn't be too hard to upgrade. And that's what I've seen personally. And obviously I cannot talk for other vendors, but I do have a little bit of insight, of course, because you run into networks that have multiple vendors deployed, etc.
The biggest issue at the moment seems to be dual stack support. It's pretty easy to find a terminal that does IPv6, but I've not been able to find a terminal that can do IPv4 and IPv6. I can actually configure that on the GGSN, but I've not been able to locate a terminal that can do that. So if any one of the people out here doing a lot of IPv6 knows a phone that will actually do both IPv4 and IPv6 within the same context, I would love to hear about it. I also tried using my Mac and hacking the PPP configuration to see if I could get it to work, but I was never able to make it work. But actually I think the mobile network would be one of the first places we could start to deploy it commercially, because we don't have a lot of old CPEs that doesn't do v6. Okay, thank you. I think I will hand over the microphone to David.
Sure.
Mic off. There we go. The mic is on. Wake up in the back.
Who are you, Ted?
I am Ted. I have a point to make, a clarification. I think it's not fair to say that the IPv6 stuff is really as close to reality as you alluded there, David, here in the States, because while all the handsets support v6 addressing, most of the infrastructure does not, and that's the challenge. And that's a pain in the ass to switch out.
Well, that's basically why I said specifically mobile networks are the ones that are actually fairly easy to support IPv6. So it doesn't mean it's easy. There's work to be done, but the actual equipment that's deployed in many places is IPv6 capable. And I definitely know that from the perspective of obviously being a vendor for our equipment.
Well, maybe you're seeing it from somewhere different, but I don't see it that way. Because I know our network, the infrastructure on the radio side, on the wireless side, the mobile network itself is the challenge. The handsets all do it.
Yeah. So, I have to specify there in the sense that I cannot talk for CDMA networks.
I just asked someone else here who runs a GSM network, and they said the same thing that I said. Maybe what needs to be pointed out is that doing mobile networks in Denmark and doing mobile networks in the U.S. are slightly different in terms of scale and geography.
Well, I honestly don't believe it's a scaling issue in this case. I mean, I've seen deployments where IPv6 actually was enabled, not visible to the end user, where it was enabled for testing purposes, and that was done countrywide. That was not like a small deployment somewhere. I cannot mention where it was, but it can be done right now. I do know that. I mean, obviously there's going to be issues, and one of the issues, of course, whenever you do something new, you're going to run into some bugs, some other problems. I mean, there's no question about that. You will probably find scaling issues because obviously, I mean, you're trying it out with only a couple of users on a big network and everything might be working fine. You're enabling more users, you might run into some issues. I mean, there's no question about that. This is very new things. If nobody else has tried it yet, I mean, there's no question that you're going to find issues. But I do know it can be done today. And yeah. But anyways, let's start. So let's first cover a few goals of this presentation. I want to talk a little bit about what is ahead in mobile networking. I'm not going to cover things like CDMA. I'm not going to cover WiMAX. That's not my expertise. There's no point then for me, obviously, to talk about that because that's just, not the thing that I know a lot about. Otherwise, I mean, the amount of time that we have available here also limits the kind of detail that I can go into. So my goal is really today to give you like a feeling for what's ahead. There will be a lot of acronyms on the slides. You won't have to understand them all. Don't worry about it. I mean, if you really want to, you can look them up in Wikipedia, which is in very good resources if it's about mobile networking. But it's all about getting a feeling, getting an idea what's ahead and what's going to happen. So first, I'm going to talk a little bit about current technologies, what is available now, the kind of speeds that you can be expecting. Obviously, that's a bit different in different countries, and especially again, the US is a little bit difficult case because there's so many different technologies deployed. And as I said before, I won't speak for CDMA and I won't speak for WiMAX technologies. I will show some real-world measurements, just a few, just to get a feel. Then after that, I will be talking a little bit about LTE. LTE is the proposal, or it's actually more than a proposal because equipment actually does exist and it can be used right now, but of course it's still very experimental. But it's supposed to be the next generation of mobile networking for 3GPP-based networks. And interestingly enough, and that's the thing about the US, Verizon has decided to go with LTE as well. So in fact, if you're talking about future networking, mobile networking at least, I cover a larger area than we used to because there's actually going to be a whole lot more 3GPP-based mobile networking in the US than there used to be. And then after that, I will talk a little bit about what LTE people call LTE advanced, and that are basically new concepts and new ideas on how to get even more bandwidth or how to get even more performance out of mobile networks. And of course, a little bit of a conclusion. So first of all, in most 3G, UMTS, GSM networks, providers have upgraded to HSPA, which is technology to just improve data performance. I hate actually personally the word data because I'm an IP guy and I much prefer to talk about things like TCP, IP, internet, etc. But data is the term that mobile people use for internet traffic really. So downlink, what you see typically deployed at this point is about 7.2 megabits maximum speed, uplink around 1.9. If you look around in the US, there are indeed similar speeds. And again, I want to say it's like, take this as order of magnitude. There's really no point in saying like, well, that's 3 megabits or it's 7 megabits or 10. It's really the same order of magnitude because there's a lot of other factors that actually determine the kind of speeds that you are going to experience as an end user. Because to say it in a different way, these are the maximum speeds that you can achieve. And somebody once told me basically, like if you climb into this radio mast, sit on top of the antenna, then yes, then you will get this maximum speed. If you're further away, there's interference, there's all kind of issues that will actually lower the practical speed that you experience. On the other hand, I mean, the top speed is important because it gives you an indicator of what is possible and what kind of speed you can achieve. And therefore, I also show you some measurements to give a little bit of an idea. Then HSPA is not like a dead end. It's like the speeds that we see now, it's possible to go further. And people are talking about 42 megabits uplink and 11 megabits downlink. And perhaps even more than that. But that's, another story altogether. So here's just a random example from a home in Finland. It's actually not my home. I don't live in Finland. I actually live in Mountain View, California. So for me, I would see completely different numbers. But this is just to give you a little bit of a feel comparison in terms of speed. Interestingly enough, you see that HSPA actually can be faster than DSL in the uplink, which is, in my opinion, actually quite an achievement, because in wireless networking, it's actually the uplink that is very hard, because you're talking very small devices that have power requirements, that are moving around. There's synchronization issues. It's actually pretty hard to get very high speeds out of like something that's moving around, while the other direction is actually a lot easier. So getting this kind of uplink speeds that are competitive or somewhat competitive with DSL are quite impressive to me, at least. If you look all the way at the bottom, there's a little picture, and there you see also an interesting limitation. You see ping takes 57 milliseconds. If you also look at the actual distance of this ping, it's only 50 miles. And then you start to realize that, well, it's all nice to talk about speed, but of course latency is a big issue as well. And that is a big, big, big handicap that we have seen in basically current mobile network deployments, is that the latency that we're typically seeing is just way too high. And of course that's making it harder to do voice over IP. That is basically the holy grail for lots of IP people, of course. The good news is that in LTE that is seen as an issue, and it's actually being actively targeted, and people are trying to reduce this latency to actually improve performance and overall user experience. This is an example of driving around, again in a suburban area somewhere in Europe. Well, judging from the previous, this is actually in Espoo in Finland. Interesting to see here is you get a little bit of a feel, we know the order of magnitude. You can do about 7 megabits per second downloads, but obviously you cannot always achieve that. If you're driving around, you get a much better idea, because you get to see a lot of different spots in the network. And what's also very nice to see in this picture, you can actually get to see some of the limitations of wireless networking. Because one of the beauties that you see here is that, well, you can have this beautiful radio link that is performing flawless. You might even get the top speed on the radio link, but if the backhaul from the tower to the network is just not enough, then you're still not going to see this kind of speed. And obviously you can see that very nicely in this picture, where there's this flat line at around 1.5 megabits per second, and I'm sure a lot of people can explain that here, why that is exactly that amount. Then we go to LTE. There's a lot of acronyms here, a lot of little words here. I'm not going to discuss them in detail. They're just here for reference. Don't worry about it. The key point is that LTE has a new air interface, which means there's new radios necessary, but those radios, of course, perform better. Of course, very complex as well, but because of that, they can get higher throughput, but also lower latency. Another important thing that you also see in all those wireless standards is that people are discussing different categories of devices. There's often category of devices envisioned that use little power, are fairly dumb, can be used for different kind of purposes. In this case, you see the class 1, class 2, class 3, class 4. It also allows for a growth path, because basically if you start usually to develop devices at the low end of those categories, and later on devices that can do more come on the market. In this particular case, it's expected that most devices will initially be class 3. So that means there will be about 100 megabits per second uplink capability and 50 megabits per second downlink capability. To show you a little picture about the architecture, it looks a whole lot simpler than what we've seen earlier in 3G and UMTS networks. On the other hand, this kind of pictures hide a lot of detail. I mean, there's still all the complexity necessary to provide true mobility. So there's still tunnels in the network, and that's still causing some latency, etc. So despite that the network looks a lot flatter and simpler, there's still a lot of minor things that need to be dealt with that you don't have to deal with in a regular fixed network. But there is one important thing here, and that's basically the bottom of the picture, and that's the eNode B, which is becoming the node that deals with all radio communications. That node will be connected using IP. So basically everything beyond the radio is talking IP. And that is, of course, something that I like a lot, because that means we can do real IP networking, and it allows for a lot more flexibility in network design. Voice, unfortunately, we have to touch that always. The good news is that LTE is really going to be signed with IP and internet traffic in mind. That doesn't mean that everything is as efficient as IP people would like it to happen. There's still all kind of legacy issues, things that need to be backwards compatible, but also the thinking in some of those standards bodies are somewhat different than other standards bodies that specialize in internet technologies. So yeah, you will still see some complexity that many people might not like it that much here, but really the end thing is it is going to be an IP-based network, and voice will be carried over IP if it's going to be carried over an LTE network. Initially, it's envisioned that LTE networks will be deployed as IP only, and that voice calls will still be carried by the 2G or 3G network, but later on it's envisioned that LTE-based calls will be just taken using voice over IP. To show you a little bit about latency numbers, if you look here at you see the commercial deployment numbers. The LTE, the evolution numbers are estimated from labs, results, etc. So always take it a bit with a grain of salt, because of course the reality is always a bit different from what people are expecting and what you're doing in labs. But you can clearly see here that reducing the latency in the network is really a goal. And if you look at the numbers, then you see that we are getting into a territory that you can really do low latency stuff or reasonably low latency stuff over a mobile network. Then we're talking a bit about future technologies. Of course, people are not sitting still, because LTE is now being planned to be introduced by 2010 for people with really aggressive schedules. 2011, 2012, 2013, something like that. But people are already talking on further enhancements, because it's nice to finally have commercial equipment, but there's, of course, all kind of ideas how to improve things. The nice thing about this kind of improvements, in many ways, they're also valid for WiMAX and other kind of technologies, because of course everybody is looking at each other and trying to implement similar technologies to increase speeds. So this is just a general picture with everything on there. I'll go a little bit more detail in the next slides. So one very simple thing is simply bundling more bandwidth. Well, you know, that is very nice, of course, but if you go from 20 megahertz and use 100 megahertz instead, of course you can have higher throughput, but of course the other thing is you're stealing bandwidth from other users on the same cell. So it all sounds nice, and it is possible, but it actually requires other measurements as well. And the other measures are basically you either have to decrease cell size, so you have less users per cell, or you have to do other things like acquiring more spectrum, or even other more complicated technologies. Then there is something called coordinated multi-point transmission and reception. That's a technology that actually turns things a bit upside down. Normally in a mobile network, you have all those cells in the open air. One of the issues that you have with that is they're actually interfering with each other, even on the cells. Of course, you try to keep those cells as far away from possible, but of course, if you put them too far away, then you get things like dropped calls when you're moving from one cell to another. So there's always a certain overlap, there's always a certain amount of problems caused by just being too close together. Well, the trick with this idea is basically that you actually start to make that an advantage by actually using those different cells in parallel and actually trying to increase bandwidth by actually reaching a mobile phone from multiple cell sites at the same time. This is obviously very, very complicated, and it's something also that only can be done if there's an optical backbone behind, because if you don't have optical, you just don't have the kind of speeds to control this whole thing and to make it work. It's very interesting technology. It could allow for quite a bit of increased speed, but it's also, very complicated. Relays. Many people have heard of probably things like nanocells and femtocells and things like that. Relays are more or less a concept similar to that. It's basically, femtocell is actually something that people envision to have like a local cell that's actually connected directly to the IP network, for example at home and using your DSL link going back to the mobile network. But another way to look at it is to build relays that can be closer to a user, that can be indoors, etc. And the more basically you have of those, the faster you can make the network and the less interference it will have. It will improve your coverage, etc. To give you an idea about spectral efficiency, because of course one of the basics of getting more bandwidth in a mobile network is really pushing more bits through the air. And one thing is, as I already touched, is like decreasing cell size, because that actually allows you to reach less people, so there's less bandwidth or less available airwaves that you have to share with less people. But of course, one of the nicest things is simply to try to encode more in the few megahertz that you have available. As you can see in this picture, we still manage to wring more bits out of the hertz that we have available, but this picture is not even close as steep as you see in this other thing. So the reality is that while spectral efficiency is still being improved with all kinds of technologies, there's still a lot more needed in the area of smaller cells and things like that to really reach more users at the same time. This is just a picture of that. I'm going to skip this one. So, in conclusion, what we're really seeing here is that mobile networks are starting to be designed for TCP/IP use. And that's a very big change from the past. I mean, all those other networks that we have seen in the past in mobile network were in one way or the other suboptimal. I mean, you saw the latency issues, especially in the GPRS and edge networks, that were actually a major problem, and also causing issues for users that basically made people not to use it because it was simply not good enough. Another thing that you're seeing now with this kind of speeds that we're seeing in mobile networking is we're starting to see some competition between mobile and DSL networks. We've heard, I read somewhere recently that in Japan, the actual growth of high-speed, fixed high-speed is actually starting to decrease and seems to be cannibalized by people who simply only buy a mobile subscription because they have this attitude, well, I'm not at home anyway, so why would I pay for this connection at home? And instead, I just spend a lot of money on my mobile connection, which is actually fairly competitive in speed already as well, and just have a single connection. The other thing that you see is those large cells seems to be a bit of the past. I mean, with the kind of data traffic that people are expecting, but also try to encourage, of course, we really need to move to smaller cells. We need to find ways to fill in between the big cells. We need to get better indoor coverage, etc. So to really get that done, we need there's a lot of building going to be required, and there's also going to be a lot of links that are going to be necessary to connect that and hook that all up. Another thing is that you see is that backhaul is going to be increasingly important. A lot of mobile operators always had something like, well, we just use a little bit of bandwidth behind the cell site. Well, those days are over. I mean, you really have to start thinking about optical, and that, of course, comes with its own price and will require quite a bit of an investment. And of course, there's the rural areas. There's areas where there simply are less users using the network at the same time. In this kind of circumstances, it's really not a big deal, and you can use less, even though your radio network might support higher speeds. And then finally, a big remaining issue that will be there in mobile networks, and that's simply radio speeds because and spectrum availability. It's like people would like to do way more, and because there's just limited availability, that's the real reason we have to do all this complexity to bring more bandwidth out of this little bit that we have available. So that's basically it.
Does anybody have any questions for David or any comments on what we've heard?
My name is Rich Brown, and how big are the cells? I mean, clearly one of the problems is if, I remember reading the WiMAX stuff, and they say, oh, we're at a 30-mile distance. Well, 30 miles is a lot of people, and if they're using a lot of data, the numbers can't work out. So how big are the LTE cells likely to wind up?
That really also depends on the frequency that you're using. So it's you can basically use it on any frequency that you have access to. So that's much more a physical property than an LTE property.
Well, but there's still bandwidth constraints that if you have
yes.
1,000 people in a cell, if your cell's contains 1,000 people, you're dividing your
yes.
feed by 1,000. Yeah.
So that's a matter of tuning. That's,
okay.
You can obviously decrease power, etc., to make your cells smaller if you want to.
Okay.
But there is, yeah, that kind of engineering depends much more on the frequencies that you're using.
Okay, thanks.
Dan Alexander. I'm going to put my Aaron AC hat on for a minute because it seems like there's some interesting variables kind of converging here. I mean, it's you got smartphones and competition between mobile providers. It seems like that's pushing IP further into mobile networks. You got network upgrades and vendor development, like it was mentioned earlier, does take time. It's not an easy thing. And someone can correct me if I'm wrong, because I thought there's something like 240 million mobile subscribers in the US right now. And IANA has 26/8s left. So, I think it's great that mobile networks are moving to IP, but I'm just kind of wondering if they picked the right version. Yeah. Are mobile providers taking some of this into consideration? I mean, you guys probably can't speak, you definitely can't speak for everyone, but are mobile providers looking at these kind of variables and factoring this into their planning?
Yeah, so I specifically didn't mention the version of IP in many of those slides. It's pretty clear that all the new technology that's being designed is designed with IPv6 in mind. Well, of course, it's not that simple. It's like as Ted also, it's like you can have the equipment and all this kind of stuff can be ready, but if you're not willing to do and actually deploy it, then you have a problem. From there, of course, I mean, it's beautiful to have an IPv6 network, but if you cannot communicate to other people on the internet who don't have an IPv6 network, it's still useless. So there's a lot of other issues, but those issues are really the same as for everybody else on the internet. I mean, we've got a big problem here. That's the reality. It's not going to be easy to go to IPv6. It will be necessary, but it's not going to be easy. And to answer that other part of the question, yes, we do see a lot of mobile operators talking about IPv6 and in fact planning for it. And I definitely have also talked to people who have even already deployed it. Not for customer use, but they have deployed it and tried it out. It does exist, but you know, we're not there yet. Ted.
All right, let's ask the really fun question. Point-to-point IP addressing, multi-user, multi-point, where do you stand? What do you think, Mr. Nokia, Mr. Vendor? What are you going to sell us? You know, we're all internet subscribers of the internet model here, yet you want me to live in your walled garden. I hate you. Why can't I do IP and IP communication on my phones?
Mr. Operator, who wants the walled garden? Is it us or you?
Both.
Actually, there's one thing about mobile networks that has an advantage. I mean, there's a certain complexity and overhead involved with all the tunneling that you see in mobile networking, but also has an advantage, because one of the advantages is that you can separate your transport plane and your user plane quite easily. And that basically means it's very easy to deploy IPv6 for your end users, but keep your own network running with IPv4 private, IPv4 public, IPv6, a mix thereof. It all doesn't matter.
They merge, Dave, and you know that as well as I do. There's no way around it. We have to have economies of scale. So, I mean, and they're merging now. I mean, you look at the new handsets and the new voice apps coming out. You run Google Voice over the top on an HTC handset. I don't need your control plane. I don't need your signaling plane. I can do VoIP-to-VoIP calls with other handsets enabled with it. Right? That is the future.
That's fine by us.
Yeah, because you're selling me the handset, right?
Well, we are the vendor of the networking gear, but of course we have somewhat of a relationship with this vendor of handsets as well. Yeah, that's correct.
So anyway, I don't know where you stand on that. Where do you see that happening in time? I didn't see it on your slide when you talk about the future, and it was a good pitch for LTE, but that's a real enabler.
Yes.
Right? So when are we going to be able to take advantage of that and enable what we really want? I understand that battery life is still a problem and CPU usage in the handsets is still a problem, but where's that in your time scale?
Well, the target is pretty clear, and that is always on and IP connectivity in your phone. And how an operator that is going to implement that, I don't have control about that. I mean, the system is designed that an operator can deploy public IPv6 addressing on a phone and even do things like IPv6 networks or prefixes or whatever. So it's enabled, it can be done, it's designed to do that.
So if I take your radio access control network and I hit your tower and I hit your base station and your RAN, your radio controller, I can do a U-turn right there if it's an IP address that it recognizes on the same cell and send it right back out?
Ha.
Ha-ha!
I
told you it was time for the fun questions.
I told you I didn't want to go in details. No, it's actually gotten a lot better, but there is issues, yes.
Issues?
Yes.
All right. Yeah. When do I get an IP routed network for my mobile network?
It's a lot more IP routed than it used to be. And,
How much proxy mobile IP do you want to buy, Ted?
I don't need to buy it.
No, but it's very simple. I mean, I started the talk already that there's a lot of legacy. There's a lot of things that I might not even consider to be pretty. But the other side of the story is it's a lot prettier than it used to be. But yeah, there's no perfection. There's definitely things that I would do different.
Okay, I think this questions concludes our session today. Thank you for coming, and thank you for your good questions. It was enlightening. Thank you. And don't forget to go to Beer and Gear now. We're a little late, but I guess they will still have beer left for us.